I'm really glad to start to do this new day. And so let's bring my pen and measure the time. So I just set the first hour. I'm happy to start.
If you write anything on your computer, you need to get Grammarly.
I write pretty much all day, every day.
Starts off with something called rational functions and simplification. What in the world is a rational function? Firstly, what's the key word to rational?
Fractions.
Yeah, that's exactly right. You guys are on the ball today. Drank extra coffee today, didn't you? Me neither. You can imagine if I did. Sometimes on the weekend I do drink coffee and then it's just off the wall. Rational functions. So some people have already said the key word in rational is ratio. If you've ever heard of a ratio, we made it in this class. What a ratio is a comparison of two numbers or two quantities, or in the simplest words, it's a fraction. So what we're going to be talking about in chapter 7 for the whole thing is functions that are fractions or fraction functions. That's what we're talking about, these fractions that we're going to be able to look at and manipulate. Now more specifically, they're not just fractions. They're fractions where the numerator, does that word make sense to you, hopefully? That's the top or the bottom number. Or the top part of a fraction. Where the numerator and the denominator are both polynomials, those things we've been dealing with so far. So rational function is a fraction where both the numerator and denominator are polynomials. Both the numerator and denominator are polynomials. So something like P over Q, where P is a polynomial and Q is a polynomial. Remember, a polynomial is just one term or more terms connected by some pluses and minuses. That's really all we're talking about. So this right here would be a rational function if I put it in a different form. That would be just fine. First, let me start with some rational expressions. Here's some examples of what we're talking about. Polynomial, It's not, what do you think?
Oh, yeah.
Sure, yeah. Polynomial? Actually, yeah, it is. If you're a little confused with that, anything, one or more terms, whether it has x or not, can be considered a polynomial. This is the most simple polynomial you can have. It's just a constant. But this is a rational, what's called expression. We haven't got to rational functions yet. I'll show you what that is. This is a rational expression. We can make it a little bit more complicated. We can do x squared minus 1 over x plus 1. That looks more like your typical rational expression there, where you have a polynomial on the top and a polynomial on the bottom. You can do it. You can have a constant on the top and something like x squared minus 5x plus 6. It's also a rational expression. Anything that
Of all
it has polynomials. So basically what I'm saying is no square roots, no fractional exponents, no i's, no weird stuff in there, and you have it in a fraction form, that's a rational expression. In order to make this a function, have you ever seen this notation? Have you ever seen that before? What's that mean? F of x is how you say it. It means a function whose variable is, that's what it is. So this just says the following thing is a function, and the variable is x. Okie dokie. That's what this notation means. F is like the name of the function. You could have G there, or H. It's just the name. Like you guys have a name, like my name is Brandon. This function's name is F. Okay, that's suck to have a name like that, wouldn't it? Well, they said you're in school, that would suck to have a name like that. Anyway, this is a rational function. As soon as we have this function notation, and then we follow it by a rational expression like x minus 3 over x cubed. That's a rational function. Now, when you were first introduced fractions, actually before you were even introduced to fractions, I know because I did this on Monday in my Math 80 class. Before you even talked about doing fractions, you learned one thing about them. Specifically, you learn that if you have a fraction, there's one thing that you can never, ever, ever, ever do. Do you remember what's one thing you can't ever do in fractions? It's not add them. You can add them. You subtract them. You can multiply them. You can divide them. You can divide them. But you can't divide by this one specific number. Zero. Can you ever have a number over zero? Can you ever have a denominator of zero? You call that undefined, right? Because you say, oh, divided by zero is like, it's like the difference between these two things. If you have 0 divided by 4, it's like you have $0 and you split it amongst 4 different bank accounts. How much is going to be in each bank account? That's fine. That makes sense to even ask that, right? If I have no money across 4 bank accounts, I have no money in any of them. That makes sense. But when you say this, I have $4, I want you to put it in 0 bank accounts. How much money is in each bank account? Do you have a bank account? That doesn't make sense to ask how much money is in each one of them, does it? So this one is undefined. You can't even answer that question. What this says to us is that just like with any other fraction, you can never have 0 on the denominator of your rational function, okay? Because it is a fraction. You can't ever have 0 on the denominator. Let me write that out, and we'll talk a little bit about that. So major note for us today. For any rational function, the denominator can never be 0. For any rational function, the denominator cannot be 0. Just like every other fraction you've ever seen in your life. You just can't have it, otherwise it's undefined. That's the next thing I'm going to write. If you do have a denominator that does equal 0 at some point, look, here's the difference between a rational function and a fraction. The difference is that sometimes the value of your denominator can change. You with me on that? So it's not always going to be 0. It might be 0 at only 1 point, or 2 points, or 3 points maybe. But it's not going to be 0 everywhere, unless there's just a big fat 0 down there, then of course it will. But if it's not, then you might have some points where it's undefined. That's what I'm going to write now. If your rational function, if your denominator does equal 0 at some point, we say it is undefined at that point. Do you see the difference between a regular fraction and a rational function? Rational functions, we don't just go undefined. We go, it's going to be undefined at like 1 point, not every point, just at 1 point. You with me on this? I'll show you how to do that in just a second. So for any rational function, of course, the denominator can't be 0, but if it is 0 at some point, it's undefined at that point. But if the denominator is 0 at some point, then the function is undefined at that point. I'm going to underline at that point a couple times so you know it's not at every point, it's just at that specific point. By the way, in fractions, is it okay to have the numerator equal to 0? Is that okay?
Yeah.
Like the one I wrote earlier. Is that okay? Sure, that just equals how much? By the way, anything when you have 0 over number, it equals 0. So some of you on, that was one of the problems on your homework, you were solving it down, you had 3y equals 0, like this. You remember that problem? and you divide by 3, somebody said there's no solution. No, there is a solution. 0 divided by 3 is just 0. Okay, so when you get that again, don't leave it at 0 over 3. Okay, it's actually just 0. So be aware of that. So yeah, it's okay for a numerator to equal 0. Okay for a numerator to equal 0. That's not a problem. Do you guys have any questions on what rational functions are? Do you get the idea here? Rational functions are basically just our fractions. We're calling them a function. That's it. There's one thing that cannot happen. One thing that can't happen is our denominators can't equal 0. If they do, at some point, we say it's undefined at that point. We're going to take a look right now at something that's called the domain. Raise your hand if you ever heard of the domain before. Raise your hand if you've forgotten what the domain is. That's fine. Okay, let's talk about domain. It's not a hard concept. I'll explain to you in like 2 minutes. Would you say this is a rational expression or a rational function? Why would you say that's a rational function? Okay, and why not just a rational expression? What's making this a function specifically? Yeah, okay, so it has a function name out there. That means it's a function. So this, if I cover that up, that's an expression. That's now a function. That's the difference. Now, we're going to talk about domain. Domain has a capital letter D. So we're going to find the domain. Here's kind of a layman's term definition of domain. What the domain is every value, every input that you can plug in for x and get something out of the function. That's really all it means. It says what are the values you can plug in and be okay, you get an output. We say domains like this. Here's how we're going to write domain in this class. This is the set version way of writing domain. You write this kind of nice looking bracket there, which is hard for some people to draw, I know that. Ends up looking like a ring thing. Okay, that's fine. Just try your best. You know, that's when you get your master's degree in math, how to do that. It's all we do. Oh, just kidding. Then you write your variable. What variable are we using here?
X.
You write your x. You write this vertical line that says such that. It says x such that. And here's how you're going to finish this off. X is a real number. I'm going to use a symbol because I'm lazy. Real number. And I'll show you how to complete that and in just a second. Firstly, the real number part. The real number. Why do we say x is a real number? Is there anything like a fake number? The answer is no, there's nothing like a fake number. But we are going to talk about what are called complex numbers or imaginary numbers. That's a little bit different. So what we're doing is we're saying x is in the class of real numbers here. Okay, a real number is every number you've ever dealt with in your whole life. So all the whole numbers, 1, 2, 3, 4, 5, all the negatives, -1, -2, -3, all the fractions, 1/4, 3/4, 7/8, all the decimals you can think of, pi, square root of 2, non-terminating, non-repeating decimals. Every number you can possibly think of, all put together, is the group of real numbers. Am I getting that across to you? So when we say real numbers, we say b, and we're going to put conditions on this. I'll show you in just a second. I want you to look back at this problem, okay? We're going to look at this problem, and we're going to think, are there any numbers that I cannot plug into this problem because it would create the one error I cannot have in fractions? And by the way, what's the one error I cannot have in fractions here? I can't have, how about the top? Does the top matter? No, numerators are fine. You can have 0 there. I'm not even going to look at I'm not even going to look at the numerator when I'm looking for a domain. Don't even care. In our other problems, yeah, we care about the numerator. But when you're just talking about domain, I don't care at all. what we're going to look at is the denominator. What is my denominator right now? Is there a number that I plug into there that is going to make the denominator equal to 0? Yeah. It's not 0, right? Because if I put 0 in there, it'd be -6. That's fine. It's not 1 because that'd give me -5. But if I plug in 6 into that, put a 6 right here. Notice how 6 minus 6 is 0, right? Is that okay to have?
No.
Yep. It's not okay to have. So what we're going to do is we're going to say x is a real number. I can plug in anything else, right? I can plug in, if I plug in 2 here, is it okay? If I plug in -6, is it okay? Is it -12? The only number I cannot plug in is +6. Nod your head if you're with me on that. It's the only number that would be bad. So we go, x is a real number, anything, and x cannot equal 6. That says if x equals 6, I get a bad problem here. I get something that's undefined. That's how you write your domain. You write x, that's from a variable, such that x is a real number, except x can't equal 6. That's basically what you're saying in this problem. Now, one way you can show you work on this without having to just think about it, what you do, this is going to seem kind of weird to you, you take your denominator, you set it not equal to 0. Why? Because what's the one thing the denominator cannot be? So set it not equal to 0. Then you solve it like you would any other equation. You add 6 to both sides, you get x cannot equal 6, and that goes right there. Does that make sense to you? So you just set denominator not equal to 0, solve it. So to find domain, you have to write the statement by the way. Set denominator not equal to 0 and solve it. And you know what, we're going to practice a lot of this next time. How do you feel okay with what we talked about today? So you feel okay with the dividing polynomials that we started with, right? And now the whole domain idea with rational functions? We're going to get on to more of that next time. Set denominator not equal to 0 and solve it. And you know what, we're going to practice a lot of this next time. How do you feel okay with what we talked about today? So you feel okay with the dividing polynomials that we started with, right? And now the whole domain idea with rational functions? We're going to get on to more of that next time. Okay, so if you do remember from yesterday, we did do that problem, and we said the domain is really all the numbers that I can plug into a function and get some.
Anak ko,
something valid out. So pretty much anything that's not undefined. And when we went through this, we said there's one thing with fractions that we cannot have, and that's 0 on the denominator of a fraction. And so when we look at the problem with domain, at least, we really don't care about numerators. We look right at the denominators, and what we know is that our denominator cannot be equal to 0. So what I told you to do is, it sounds a little weird, but set your denominator not equal to 0, like this, and solve it. This will give you the point or points that you cannot plug into your function. Are you with me on this? Everything else will work except this point. So we add 6 to both sides, and sure enough, we get x does not equal 6, and that's what we had there originally. And that makes sense because 6 is the only number I can plug in when the denominator does equal 0. That's our problem. Are you with me on this one so far? All right, let's practice a couple more to see what the hang of this. And again, we're looking for domain. If g of x equals x squared minus 9 over 4. Hey, by the way, is it okay for the numerator to equal 0? The numerator, that's the top of our fraction. Is that okay? Yeah. Okay. How about the denominator? Is this denominator ever going to equal 0? No. Okay. So when we write our domain, here's how we start it out. We say the domain is, we're going to write the same thing every single time. X such that x is a real number. And we would put any problems that we have. Now I'm going to ask you a question. Is it okay if x equals 4? How about negative 4? If I plug in negative 4, I know there's a 4 right here, but if I plug in negative 4, is the denominator going to be 0? Then I don't care. Yeah, it's fine. How about 3? Plug in 3. Is that okay or not? Is the denominator going to be 0? Then that number's fine. Okay. It's only the denominator that I'm checking for with the domain. That's it. Just the denominator I'm checking for with the domain. If the denominator is not 0, your numbers are valid. So can you see up here on this problem that no matter what I plug in, this number is never going to change? Are you with me on that? No matter what I plug in. That means that this denominator will never be 0, which means that any number works. How we say that is x, such that x is a real number, and we're done. So this says, in a nutshell, any number will work. If you plug in anything, you'll get something out of it that's valid. Even if we get 0, that's fine, but you will get something out of it. I think we'll understood that one. Why we don't have this. Why we don't have this part of it? Well, you had a variable down here. If you plug something into that, specifically 6, it's going to be 0. Here, you don't have a variable. It's a constant. That number's not going to change. That number's never going to be equal to 0, no matter what I plug in. Follow? Okay, I'd like you to try one on your own. Just so you get the hang of it, I want you to find the domain for h of x here. So we're going to write the capital D. We're going to write the same thing, x such that x is a real number. And then you're going to find out if there's any points that are problems here. Hey, is this problem all real numbers like the last one was?
No.
Or do we have problems here? Yeah, some people going yes, some people going no. Well, we got to look at one spot specifically. Do we care about, for domain I'm talking about only, do we care about the numerator if I'm asking for domain? What I care about is the denominator, that's right. And the question is, are there any points, any values, that are going to make this part of it 0? And yeah, that's great. And the way you find that out, because this is very easy, we can do this one in our head, but the process is, what we do is we take the denominator, just the denominator, and we set it not equal to 0. Why do we set it not equal to 0? Because that is the one thing that we cannot have it equal to. Are you with me on that? It's kind of a weird thing, we set it not equal to 0. But when we solve that down, that's okay. That works out for us, and it goes right here. So if x plus 2 cannot equal 0, and you solve it, that means you're going to subtract 2 from both sides. And you're going to get that x cannot equal negative 2. Why it cannot equal negative 2 is because if you plug in negative 2, look what happens. Put negative 2 there and do the math. How much do you get? Is that a problem? That's a big problem. So we set the denominator not equal 0, we solve it, and we get this piece of the puzzle. And we write, we finish off x is a real number, that means everything, but we go and x does not equal negative 2. So we finish that off. Now what would happen in this case? We have like h of x or f of x, whatever. (5x plus 4). This is what I'm going to see if you were really paying attention to what I was saying over here. Because if you just look at this and go, well, yeah, Mr. Leonard, these are easy. That one's 6, that one's negative 2. Duh. Plug that in, you're going to get 0. I know that. Well, can you do that here?
No.
Not so much. I mean, unless you're like really, really quick, and some of you are, just go, oh yeah, that's going to be, I don't even know. But you got to do the math on that. I think I know. But we'll find out. But the idea is the same as doing this step and doing this step. Okay, that's what's going to lead you to this problem. So when we look at this problem, we're asking for the domain, which I am again. Again, we're going to write x such that x is a real number. That pretty much says everything, and then the next part says your exceptions, your constraints, if you will. Now, what are we going to set not equal to 0? The top, our numerator, or the bottom, our denominator? For domain, we do not care about the numerator. For other problems, yeah, of course, we're going to include the numerator. But for the domain, we don't care about that. The top can be 0. It's the bottom, or denominator, that we cannot have equal to 0. And so what we're going to do, just like the last couple of examples, we're going to set that denominator not equal to 0, and we're going to solve it. But guess what? Hey, have you solved things like that before? Sure, that was your C.1 homework, right? When you remember how to solve something like this? How do you solve something like this? That's right, both of you are right. Factoring, which in this case is going to be the diamond method. Now, I do need to show you something. I don't have your homework back today. I forgot it. It'll be back tomorrow. But I need to show you something about whether you have the extra step or not. And this is a great problem for us. You do remember how to factor, right? Instead of the diamond problem, I hope. And what goes here is the -3 and the -10. You see, a lot of you are spending a whole lot of extra time. Firstly, do you know how I'm getting the -3 and the -10? Okay, -3, that middle number goes here. 1 times -10 goes here. A lot of you are spending extra time doing that extra step when you don't have to. If you don't have to do the factor by grouping, geez, don't do it. That takes like 2 minutes. You don't want to waste your time, right? I'm saving lives here again. So what kind of guy I am? So you don't want to waste your time if you don't need to, right? This is just wasting time on a test or something that you spend checking your answers or whatnot. So in this case, when you look at this problem, if there's no coefficient besides this 1, you do not have to split the middle term and use grouping. That is a waste of time for you. Am I getting through you? You go directly to your factors. If you do have the number up front, then yeah, you do. You split the middle term, then you factor by grouping. That's the only way you can do it in this class. So after you find these numbers, by the way, have you thought of these numbers as rambling on there? Good. We're going to double check, make sure we get this right. -5 plus 2 is -3. Yeah, that works. -5 times 2 is -10. Yeah, that works too, so those are the right numbers. Here's what I'm talking about, the extra step versus the not extra step. Some of you are still doing this. Please watch on the board. Some of you are doing this and still doing x squared minus 5x plus 2x minus 10. If you're doing this step on this type of a problem, you're wasting your time. You're wasting it. You're wasting it. Are you with me on this? You're wasting your time. You don't have to do this. This is too much work. If you had a number up front, yes, you would be doing this step, but you don't. All you're going to do now is go x minus 5, x plus 2. You're going to go directly to your factors themselves. And why does that work? It's because we don't have the number up front. That's why. It doesn't hurt us to do this. If you factor by grouping, you can still do it. It's just wasting your time.
I wasted a whole bunch of time.
Wasted a whole bunch of time. Some people waste a whole bunch of time because they do this every time, and you're going to get the same. You're going to get the same thing I proved to you right now. If you factor this out, you get x times x minus 5 plus x minus 5. Look at it. X minus 5, x plus 2. But you don't need that. Okay, this is kind of a waste of time. Now, can you do the extra step every time if you really, really want to? Sure, but if you want to waste 2 minutes of problem, then do it that way. If you want to be quicker on a lot of cases and just get this stuff done, then when you don't have a number out front, you go directly to here. If you have a number out front, you go and you do this stuff. Not just if you're okay on that. There's 2 cases. Number out front, that's no number out front, that's okie dokie. Review that lesson on factoring if you haven't done so already online. You've been doing this stuff. It's on there, I promise. So all the C.1, there's like 11 parts to it. They're all 14 minutes. The factoring's in the middle of that. So look through that. Okay, now, when we continue, we know about the zero product property, which will still work. We'll do x minus 5 equals 0. We'll do x plus 2. Actually, not equal to 0. And if we solve that, we're going to add 5 to both sides. We get x cannot equal 5. And x cannot equal -2. I'm just adding 5, subtracting 2, and we get those 2 pieces of code. This part you should feel okay on, right? Because we've done this already. This is our review. This was review when we covered it. This is now review of our review. So double review. Right? How we feel okay with getting these points. Solve on that. Okay. Now, what we do with that, same thing we did with this one. It's only in this case, how many points are not going to work? How many values are not going to work in my function? Yeah. In fact, if you plug those in, the reason why they don't work, check this out. What's 5 squared? Minus, this will be 15. 25 minus 10, and then minus 10. That's why this one doesn't work. Same thing happens with the negative 2. You do 4, negative 2 squared is 4. You would do plus 6, negative and a negative, that's plus 6, that's 10, minus 10 is 0. So again, that one doesn't work. That's why we have two values that don't satisfy our function, they're undefined. So we'd say x is a real number and x does not equal 5. And you just list them out. X does not equal negative 2. Close our bracket, that's how you find domain. Do you guys feel okay about finding domain? Dr. Jeff, you do, you feel all right with this? Okay, so the whole idea is set the denominator not equal to 0 and solve it. You might have to factor, you might not. On your test, you will have a domain problem. So if you want to write this down, you will have a problem like one of these three. Probably not that one because there's no work to it, but one of these two on the test. Do you guys have any questions about domain before we go on?
So if it's just a number at the bottom, is it pretty much going to be like, that's it right there?
If there's no variable on the denominator, right? That means the denominator can't change. If the denominator can't change, yeah, you're good. I mean, here, yeah, here, no, it can't change. Here, yeah. Here, of course.
Yeah.
And here, yeah. But this one, that denominator is never changing from 4. That means you're going to get all real numbers. Anything is going to work there. That's a great question. Any other questions?
Will we ever come across a case where we'll have like 10 to the 0 minus 1 as a denominator?
10 to the 0 minus 1.
Yeah.
No, well, that inherently wouldn't be a function, right? Because it's completely undefined everywhere. So I won't ever give you something like that.
We won't find that for a domain problem.
Not for a domain problem, no. If you do, then you say this function is completely undefined. It's 0 always, because that wouldn't be changing. Like if you had, well, if you had 10 to the x minus 1. Now we haven't covered exponentials, but if that x ever became 0, then it would be undefined 0, but everything else would be fine. Okay, that's a good question. Any other questions? Let's go on to simplification, all right? Move away from our domain for a while. We had a bit of it though. Here we go. So we're going to learn how to simplify some rational expressions. Now, because rational expressions really are fractions, just some polynomials, we can simplify them very similarly to fractions. You know, we can simplify fractions, right? So we're going to learn how to simplify some rational expressions. Now, because rational expressions really are fractions, just some polynomials, we can simplify them very similarly to fractions. So you know we can simplify fractions, right? I hope you know we can simplify fractions, right? Okay, good. Got that. So you tell me, can that fraction be simplified?
No.
Okay. That's the right answer. Very good. Can this fraction be simplified?
Yes.
What's the difference? What happens here that doesn't happen here? Okay, so
They don't have a common
factor. Yeah, you guys both said it. So we're looking for common factors. That's how we simplify fractions. If the numerator and denominator have common factors, we simplify it. We can simplify that by making a very fancy 1 out of it, basically. I'll show you that in a second. When they don't have common factors, we say it's reduced and simplify and we leave it alone. We're going to simplify our rational expressions exactly the same way here. So these can be simplified when the top and the bottom, our numerator and denominator, have common factors. So we're going to simplify when the numerator and denominator have common, I underline factors there. Factors. Because that's what we're going to be looking for when we get to our rational expressions. It's factors. By the way, how do we do this? Let me give you another example. Can this one also be simplified?
Yeah.
What is the shared factor here? 5, yeah. 5, and the way we actually do this, I know you guys are used to just crossing things out, right? Which is awesome for fractions like this. But really, when you think about this, how you were taught how to simplify. You were taught, okay, I'm going to write 15 and 35 differently because I know 5 goes into both of them. I'm going to write this as 5 times something and 5 times something. You with me on that? And we're going to do 5 times, well, this is a 3 up here, and this is a 7 down here. Because our answer is going to be 3 7s. So what we're really doing is we're taking this common factor and splitting it off from our fraction. We're going the opposite of multiplying fractions, basically. And we're doing 5 over 5 times 3 over 7. You know, you can split up fractions that way. That's possible with multiplication. You go, oh, okay, how much is 5 over 5? It's a very fancy 1. Yeah, 5 over 5 is 1. So you have 1 times 3 sevenths, and we all know that 1 times anything is just that anything. We get 3 sevenths. That's how simplifying fractions actually works. But you don't just cross stuff out. Yay, this is fun. I get to cross stuff out. But we do cross stuff out typically. We don't show all this work. But this is why it works. This is the why. This is the foundation for simplifying our rational expressions. I'm going to show that to you right now. Did you understand this, by the way? So really, we are simplifying by removing factors of 1. This is a factor of 1 here. That's what we're doing. Hey, would you be able to find the domain to that problem? I'm not going to ask you that right now. I just want you to think about it. Would you be able to find the domain to that problem? Think about that as I'm writing, as I'm erasing this over here. Are there 1, 2, or more points that are not going to work in this expression? It's more than 1. We're looking at the denominator, right? We're not looking here, we're looking here. You can plug in what inside the word? 2 and also -2, because when you square that, it becomes 4 as well. So yeah, that's 2. Okay, so here's what we're going to do. I'm going to give you your steps as well. Steps for simplifying your rational expressions. The first thing you've got to do, and this is why I underline this word right here, if we're supposed to simplify out common factors, how are we going to do that if our expression is not, finish the sentence. If we're supposed to simplify common factors, how are we supposed to do that if our expression is not completely factored? You're going to have to factor that, right? Because we're going to try to match up common factors like here. We're going to try to match up common factors. The first thing you have to do in order to see common factors is you got to factor it, which is why we spent so much darn time factoring in this class, which is why we did the review first. I need to make sure you know how to factor, otherwise you're going to plummet in this class. You have to know factoring very, very, very well and get it right every single time. So factoring, that's a huge part of this. And so the first step when we get to chapter 7, essentially, is factor. And what I mean is factor both the numerator and the denominator completely. Let's do that together, okay? I'd like to factor this thing. Let's look at the numerator. Now the numerator is x plus 2 squared. Can I factor that at all? I don't mean distribute. That's not what I mean. I mean make it even more simplified. Can I do that? X plus 2. I could do that. I could separate x plus 2 times x plus 2. That's possible. I can do that, or you can leave it alone. Either way is fine. What I mean is, can I factor the x plus 2 anymore? No, it's not it's two terms, right? It's not a difference of squares, not the sum of cubes, not a difference of cubes. It doesn't have a ratio common factor. I'm done with that one. Let's look at the denominator. Can I factor the denominator? Is there a GCF? You look at that first.
No.
GCF is something that divides both terms. Is there that?
No.
It has two terms. The thing you check for two terms, is it a sum of cubes, a difference of cubes, or a difference of squares? This is one of those three. Which is this one? Definitely a difference of squares. I hope you're seeing the difference of squares really easily on this. I don't know if we factored this particular one or not, but we're going to have the x plus 2 squared. On the bottom, you need to know that a difference of squares, whenever you can write this as, let's do x squared, and how am I going to write the 4 to make it look like a difference of squares? 2 squared, very good. So this could be written as x squared minus 2 squared. And we found out a way that we could factor this every single time. It's not a problem. We factor this as x. A lot of people get confused with x minus 4, x plus 4. That's not it. That's not it, folks. It's going to be x minus 2 and x plus 2. That's how you multiply and you get that 4. You with me on this? So we're going to do x minus 2 under same sign, different sign. That's how you cancel out those middle terms when you distribute again. Just by show of hands, how many people are okay with the difference of squares? Good, very good. If you're still a little bit like, how in the world are you getting this? Come and see me. Or refresh your memory by looking at that video the very first time we did factoring. It's on there. So we go, all right, well, I know that x squared minus 4, and you're going to be able to do this without this step after a while, is x minus 2, x plus 2. We can double check it. X squared plus 2x minus 2x, that cancels, that simplifies 0. Minus 4, and that's exactly what we have here. So the very first step is we're going to factor the numerator and denominator completely. This one was done. This one was a difference of squares. We have that right here. Nudge your head if you're okay. Okay, good. The second and the last step is what we're going to do now is we're going to cross out, we're going to simplify out any common factors, not common terms, common factors. I'll show you the difference in just a second. But write this down, write this down. You're going to simplify common factors. Not common terms. Not common terms. So let's do this thing. Do you see any common factors up here? Things that are exactly the same on both the numerator and denominator that are factors. Factors are things that are multiplied together. So multiplied together. So this right here and this right here, these big pieces, notice how they're being multiplied? Those are factors. What you can do, you can simplify all of a factor or nothing at all. You can't go through and simplify part. For instance, here's what I mean by terms. This right here is a term, that right there is a term. That's a term, that's a term, that's a term, that's a term. You with me on this? What you can never, ever, ever do is factor something or simplify something that's connected by an addition or subtraction, because that is a term. So what you could do is cross out the twos. You can't do that. Those are terms, those are not factors. Factors are pieces that are big pieces, typically, that are multiplied together. That's it. You okay with that? You sure? Shake your head if you're not. Okay. So do we have something that's exactly the same? Two similar factors. We have one of them here. Now, if you wrote this as two different ones, that's fine also. That doesn't really matter. We can simplify this out just like we did the 5. That one's gone. Are both of these gone? Just one. So I'm just going to simplify that squared portion of it. That's leaving me 1x plus 2. How many times do you think that would happen in a row? That's like a quarter ending landing on edge. Okay. So do you all agree that there's an x plus 2 left on our numerator? What's left on our denominator? Okay, important question for you. Can I simplify these x's? No. Do you notice how these are not factors? They're being added and subtracted by that number 2. These are terms here. They're not factors. Factors will be multiplied. Typically, for us right now, they're in parentheses or they're at the beginning of our problems. Right? They're not included within our parentheses. That would be terms. We're completely simplified there. X plus 2 over x minus 2. Let's try a few more, all right? Get some of these under our belt. Okay, right off the bat, I got a question for you. Would it be okay to simplify the 3y cubed with this 3y cubed? Is that okay or not? What do you think?
No.
Clearly no. No. This has a subtraction right in front of it. There's no way we can simplify that. We can't even do, look at the board, we can't even do the y cubed and the y cubed, right? Because this piece still has that subtraction right there. It's got to be completely multiplied. So everything or nothing, that's the idea. So what we're going to try to do is factor this thing. Does the numerator factor? Numerator is how many terms? Can't really factor one term. We're going to leave that alone. How about the denominator? Does the denominator factor?
Yes.
Sure. That actually has, what's that called again when you have something similar to both terms? You say that? That's right. Greatest common factor with a GCF, this has one. So let's factor out the GCF. Let's look carefully at the denominator. What's the number that goes into both these terms? How about the very large variable that's common to both? So we're going to factor out 3y cubed. Remember factoring, we're creating parentheses. This should be like old news to you guys, I hope. If you factor out 3y cubed from our first term, do this on the side if you want to, or do it in your head, this is how much? Good. And then we'll have a minus how much? 1. Very good. Are you okay on getting the 2y minus 1, folks? Good. So we factor out 3y squared, or 3y cubed, I'm sorry. We're going to get the 2y. We're going to get the minus 1. And now we're going to look for any common factors on the numerator and denominator. Do we have any common factors on the numerator and denominator? Yes. This isn't being added or subtracted by anything, right? We can simplify that. That's great. This is like a factor itself. You can pretend it's multiplied by 1 if you want, just to make sure you know it's a factor. This thing is a factor. It's being multiplied by this entire expression. Are you with me on that? It means this is a factor, that's a factor. They're exactly the same. This is the best part of the class. We need to make things better. Darn.
So do you have to change the sign because the other one's at the bottom? The 2y minus 1?
Change the sign. No, we don't have to change any signs. What I am going to ask you is this equal to 2y minus 1 like that? No. Explain that.
Because 2y is on the bottom, not on the top.
So since this is on the denominator of fraction, we can't magically just move it to the top, right? We're not Harry Potter. We don't have like a math wand. Bam! That'd be awesome, but I don't have that. I've got the glasses, but not the... More like Voldemort anyway. I'm just kidding, I'm not. I had an Harley face. You see that? See the movie? Crazy movie. Anyway, so the problem is yeah, we can't move this to the this would be a numerator fraction. That should be like just the value itself. We can't do that. What actually happens here is that when we simplify, just like we simplify here, we get 1s, right? We get 1 over 1. And so this would become a 1, which is why we're getting the 2y minus 1. But this is also a 1, so be careful. When you simplify, you will get stuff like this in your homework. Don't just eliminate the numerator and put the denominator. If you eliminate the numerator, you really haven't eliminated it, you just made it a 1. And so this is 1 over that. That's the proper way to write that. And the denominator, and then we're going to simplify common factors, not common terms. Let's try, we're going to have several more of these things. Let's try a couple more right now. I'll show you one more thing, do 2 more after that, be about done. Yeah, we like those ones, right? Can we simplify anything the way it is right now? What about the x squared and x squared? Can we just cross those out? We'd love to, but no, we can't. It has to be, look like it's in parentheses or at least be a factor, something like we've had before. So what are we going to do with this problem if I'm asking you to simplify it? How do we factor these things? Say it again. Let's do the time method. Now here's the question. We just learned this. We relearned this like 10 minutes ago. Do I need the extra step to split the middle terms or not? In this one, yeah, I do. I do need the extra step. Don't waste your time when you don't, but you do here. Take 2 minutes. See if we can factor these. You should be pros at this right now. Almost every homework assignment, besides that last one, has had factoring in it. I hope you remember how to set this up. Just help me out with this one step. What goes on the top for our numerator? Okay, and on the bottom?
1.
Just making sure you remember how to do that. The B goes here, the A times C goes here. Boom. Yeah. This is pretty much like 3 problems in one. This is why I said you gotta learn how to factor correctly, right? Because if you don't know how to factor this, how are you supposed to simplify it? In the other one, you need 4 and you need what was down here? You multiply those. You multiply those. A times C. Okay, we're about to get going on this thing. Let's get started up here on the board. If you're still going, cool, work on it. Make sure you can factor these correctly. Okay, so up here, we have the -6 and the 5. Are you okay getting those 2 numbers, folks? Good. We're going to find two numbers that add to -6, right? And multiply to 5. The only things that multiply to 5 is like 5 and 1. That's it. So I know they both have to be negative because this is a positive and that's a negative. So we're going to do -5 and -1. Did you get -5 and -1? Good. We cannot do this in this particular case because we have a coefficient of 5. We just covered that again, right? So we can't do this one here. But what we do is we split that middle term up. This is where I said we have the extra steps. So we have the 5x squared minus 5x minus 1x. I'm going to put the 1 there just to make sure we see that. Plus 1. And we're going to factor by grouping. So factor by grouping, we have 5x we're pulling out of that. We're factoring that out, we get x minus 1. Over here, notice we have to factor out a negative. Do you guys see that? We're going to factor out a negative, and the only thing that's going into both is 1. We're going to get x and minus 1 again. The minus, because we factored a negative out, we're basically dividing by a negative that's changing the sign. We have exactly the same thing here. That's what we wanted. We're going to get x minus 1 and 5x minus 1. How many people made it that far? If you didn't, go back and work on this on your own next time. See that you get that right. You have to. Okay, next one we have 4 and -21. I'm looking at that. I'm seeing a 7 and a 3 somehow. Are you seeing a 7 and a 3 also? Probably seeing a positive 7 and a -3. Again, we have to split our middle term up. 3x squared plus 7x minus 3x minus 7. We're going to factor. The only thing that factors out of our first two terms is x. We get 3x plus 7. What factors out of our last two terms, it has to be a negative because we have a minus there. The only thing that's going into both is 1. So we're going to factor a -1. I'm going to put the -1, and I'll have 3x plus 7. Again, those signs change because you're factoring by a negative. Get used to that. That happens a lot. Are you okay so far with that? When I factor by grouping, I get 3x plus 7. I get x minus 1. And I'm done. I factored that stuff. How many people made it down on both of those? Good. If you didn't, if you're like, oh my gosh, I messed something up, please go back and fix that. Go back tonight and work on that. Your factoring's, right now, it's the biggest thing you can do. It's the biggest thing you do. Simplification is easy if you know how to factor. Multiplication, division of rational expressions is easy if you know how to factor. Addition, subtraction, well, we have some other stuff to do, but the simplification part of that is easy if you know how to factor. If you don't, you're going to struggle with all that stuff, and I can't afford to have you do that. So you need to be mindful of this. Okay, now we're almost done. What we're going to do, we're going to take these factored versions, we're going to put them back in our fraction form. So from our numerator, we have the x minus 1, and we have 5x minus 1. From our denominator, we had 3x plus 7, and we had x minus 1. If you didn't get these right, can you fold it down and see that this is the appropriate way to go? Are you guys all right with that? You sure? Okay. Now, do we have any common factors? Is there anything we can simplify? Okay, that's great. X minus 1s are factors because they're multiplied here and here. We can take the entire factor and simplify it out. That's what we want to do. So x minus 1s are gone. We're going to get 5x minus 1, 3x plus 7. Can we simplify any further in this problem? If you could, you would have done it here. Okay, this takes care of all your simplification at once, provided you completely factor. How many people are okay with that? Who are with this one so far? Good, all right, that's fantastic. Yeah.
So when we simplify and we move over to our final answer, the parentheses just disappear.
If you have just one factor, you can do that, yeah. Because it's just saying, this is my factor, right? You're multiplying by 1, that really doesn't make a difference. It's a great question. If I had like 3 factors and I just simplified one of them, yeah, you'd want to keep the parentheses. Okay, let's end with this one. I want you to work on one on your own. Just see what happens on that. What's your factor if you need to, and simplify. I see lots of good factors. That's great. Fantastic. Well, factors out of here, I hope that you saw this. You factor out of 5, and the largest power of z that's common to both is z to the third. Did you get that?
Yeah.
You have 2z squared minus 1. Did you factor that correctly?
Yes.
Good. Now, does anything simplify it?
Yeah.
The 5s? Sure. 5s do. Z's? Yeah. Look at it. Now, what you have here, really, you could think of it like this if you wanted. You could think of it as 5 divided z to the third. 5z to the third times z. You could think of that. Isn't that 5z to the fourth? And that gives you a, oh, you know what? These are all gone. I have z left. Or a different way you can think of it, 5s are gone. All but 1z is left. So what's going to be on the numerator of our fraction? Just the z. That's right. 2z squared minus 1. One last question. Do these z's simplify?
No.
But they're right on top of each other.
They always make it by.
Can't do that. The minus 1. Okay. We'll talk about one last thing right now. This will lead us into what we're going to do tomorrow. How much is that? Explain that. It is, right? Why? Because when you do addition is called what when you do this? You could switch that, couldn't you? Because it doesn't make a difference, because it's addition. No problem. That equals 1. Does the same thing happen with that? Because subtraction is not commutative. Subtraction says when I do this, the signs go with those values, so I'm going to get negative x plus 5 over x minus 5. Now that's clearly not 1. That doesn't equal the same thing. But there's one thing we can do to simplify this. What we can do whenever you are off, notice how our variables and our numbers are exactly the same, but every sign is different. You guys see that? When that happens, what you can do, factor out a negative 1. Factor out negative 1. If we factor a negative 1, just like we factored a negative 1 from over here, all that's going to happen, look at the board right now. So you're looking. When you factor a negative 1, all that's going to happen is both signs change. Do you guys see that? So if we factor a negative 1 from here, let's factor -1, and what we're going to get is instead of -x, we'll get x. Instead of +5, we'll get -5, all over x minus 5. Now, do you see that the x minus 5s are factors? You can simplify that. And our answer, that's negative. So when our signs are different, but the values are the same, like s and y, like we have an x and an x and a 5 and 5, but the signs are different in each case. Factor -1, and then you're going to see that. Here's the big kicker that we're going to use next time. Just write this last statement down. What we're going to try to do when we're factoring is make sure the term with the largest exponent is positive. Make sure the term with the largest exponent is positive. That's what I did here. Look, x was negative, so I factored a -1. If you make sure the term with the largest exponent is positive, your life becomes easier. You can factor things way easier. So what I want you to do is factor to make the term with the largest exponent positive. That'll help us out. That'll be on next time. As far as your homework goes, you're not going to have any new homework. Yay. Like you said, what I'm going to do is I'm going to put the assignment on the website. That way you have to go there to get it. If you know where the website is, you got to go. It's what I gave you the first day without the second S. It's this.
Is it due Monday or is it
Okay, just so you know, everything is lowercase. I just can't write in lowercase. So just everything is lowercase. It's sites.google.com /site singular /Professor Leonard 57. Just like this. It's all one thing. You go to the top of your website browser, you plug that in, it will come up. Go ahead and find that. The homework's not due tomorrow. It will be due on Monday because we're not done with this section, okay? Remember I told you at the beginning of class that I would give you the assignment before it's due if we didn't finish the section. So the assignment will be on there this afternoon. If you want to get a head start, which I very much encourage you to do that, go on the website and get it from there. All right, guys, have a great day. I'll see you tomorrow. All right. So I did say to make the term with the largest exponent positive. And with that in mind, let's look at the next example. That's going to be this one. Now, here's what I mean by that. When we look at this problem, of course, the first thing that we do when we simplify, I gave you these steps last time, is you have to factor both the numerator and denominator, because what you're going to be trying to do is simplify common factors, the factors that are exactly the same. Now, remember, it's not common terms, right? So we can't just arbitrarily cross out x squared and x squared. We can't do that. It's things that are multiplied together that are exactly the same on the numerator and denominator. And that means we have to factor first everything. So when we look at the bottom, we might be able to factor that one pretty easily with the diamond method. You guys see that already?
Yeah.
Is this going to have an extra step or not, do you think? No, this is going to be pretty easy. The top one, though, would you look at that, and look how the term with the exponent there, term with the x squared, that's negative. It has a minus in front of it. What we want to do to make this easier on ourselves is factor out a greatest common factor from that, but also take the negative out. Make that positive, because otherwise it's going to look like you can't simplify some things that we're actually going to be able to simplify. I might show you that in just a second. So let's look at the numerator here. Can you tell me what factors out of 20 minus 5x squared? Okay, we're not just going to take the 5. We're going to take the negative 5. Okay, now here's how that's going to look. Watch carefully. If we factor out 5, we're going to get 4 minus x squared. You see that? That's not exactly what I want. What I want is to make the x squared term positive. Make x squared term positive. And you're going to see why in just a second. Right now, this is probably not apparent to you that this is a difference of squares. Do you see a difference of squares here? Some of you might. Some of you are like, what are you talking about? It doesn't look like a difference of squares to me. But if you factor out the negative 5, check it out, and rewrite this. Bless you. If you factor out the negative 5, you get, instead of 4, how much do you get there? Good. And we're dividing, and you're going to get plus x squared. You factored the negative out of it. It changed both signs inside. You with me on this, folks? How many people are with me on that step right there? Good, okay. Now, the last question I have for you about this, is it okay if I include the signs, but flip these things around? Is that okay? So instead of negative 4 plus x squared, can I have x squared minus 4?
Yes.
Okay, I'm going to do that. So negative 5 stays there. X squared minus 4. The reason why we do this thing is a whole lot easier to work with than this thing is. For most, than the thing I had here before was. For most people, this is a lot easier to see that that's a difference of squares. Can you see it now a little bit easier? Yeah. And you know what? We're going to have to factor out a negative anyway. You're going to see this in a second. You're going to have to do that. So you may as well do it at the beginning rather than at the end. You're going to do it anyway. So do it at the very beginning. It's easier to work with, and you don't make any mistakes on it. So we have the numerator done. Let's work on the denominator now. With our denominator, can we factor that thing?
Yeah.
How? Okay. So let's do that. Can y'all tell me what number goes on the top, please? And on the bottom? We look for 2 numbers. I'm going to start doing these more quickly because we've been practicing this for now, like every section we've done here. The 1 and the negative 6, we're going to get 3 and 2 somehow. Yeah, it's going to be. Now, do I need to split this up and factor by grouping? No, this goes directly to my factor. So right here, I write x plus 3. I write x minus 2. And I can continue that on. Now, we did say factor completely. What we've done so far, we factored out the negative out of the numerator, the negative 5. We factored the denominator completely. You can't do anything more with this. But there is something more I can do with that, the x squared minus 4. Do you remember how to factor that thing? How many people do remember how to factor that thing? Hope that you do. That's the difference of squares. And you're going to start seeing this quicker and quicker as we go through this. going to take a little trip down here and do the factoring underneath this problem. So if I look at x squared minus 4, remember that a difference of squares is a difference of 2 squares, which means I'm really thinking of this as x squared minus 2 squared. Same thing, right? And we've done this problem before in this class. When you factor a difference of squares, you end up getting 2 parentheses just like here, but it's already kind of given to you what you're going to have. You're going to have an x in both spots. You're going to have a 2 in both spots. Not a 4, a 2, the thing that's actually being squared. That's the number you put there. I gave you the form a squared minus b squared when I first introduced this. So this acts as our b in this case. We have a 2 and a 2. Notice when we multiply, that's giving us the value of 4. You with me on that one? Boiler. The only thing you have to remember is that one of these signs is a plus and one of these signs is a minus. That's how you factor a difference of squares. So this is going to go on the top with this negative 5. So the negative 5 is still there. We factored this as x minus 2, x plus 2. So let's take a little recap about what we did. We noticed that we really do want to make the x squared term positive. If we do that, trust me, it's easier to work with. I'll show you in a second. If you really need me to prove it to you, I'll show you that in a second. So we factor out the negative, making that x squared term positive. We're going to switch it around to write the x terms first. That way it's easy to factor. So that's the only thing we're doing from here to here. I switch these terms around. On the denominator, diamond method, because we have 3 terms, no problem. There's no extra step. That's actually a pretty easy one. We get down to here, we make sure we factor our numerator completely. That's the difference of squares. And now we're all the way down to here. Each of these factors is factored completely. How many people okay getting down to that point? Good, all right. Is there anything else that we can do? Cool. Do we cancel, like you say cancel, right? Love to cancel stuff out. Do we cancel or simplify common terms or common factors? Terms are these things. Terms are these things. Factors is this and this and this and this and this. Terms are added and subtracted. Factors are multiplied and divided. What do we want? Simplify factors out. Entire things or nothing at all. That's all we're doing. So here, since we have our x minus 2's, you all see that. Those are gone. Just rewrite whatever you have left over. You don't need to distribute. You spend so much time factoring. Don't distribute that back in. Just leave it. We spend a lot of time factoring in this class. Leave it factored. Negative 5 times x plus 2 all over x plus 3. You'll notice I had to leave the parentheses here because that negative 5 is up front, but here I don't need the parentheses because that's the only factor we have left. You feel still okay with this? Okay. Now, I would like to show you why this step is kind of important. Would you like to see it real quick? Okay, here's the why. Let's say that I didn't factor out the negative 5. You're still going to do the problem. However, you're still going to have to factor out a negative 2. You'll see what I mean. So if I go right down here, and I factor out a positive 5, I'm going to get 4 minus x squared over, this thing's going to factor exactly the same. This actually still is a difference of squares, only it doesn't factor as x minus 2, x plus 2. What it factors as is 2 minus x, 2 plus x. Do you see the difference there? Then when you have down here this x plus 2, my question is, do these things simplify? No, they're not exactly the same. But this is the thing I gave you last time that said, oh, you know what? If you have the values, the signs are different, you have to factor out a negative 1 here to make them the same. Do you remember that from last time? So you got to do it anyway. So right here you go, oh, okay. From here I need to factor a negative 1. And people seem not to really grasp this concept as well, which is why I give you this way. Because you have to do this. If you go, okay, I'm going to pull the negative 1 out, but what it's going to do is make that a negative 5. Do you see that? This one is going to become x minus 2, and then 2 plus x. And a lot of people ask me, well, how do you get from here to here? What are you even doing? And the thing I'm doing is I'm factoring out a negative 1. It's changing both of these signs. I'm reordering it. The negative 1's going out front. Now you can't simplify those and we get exactly the same answer. It's only these two things are switched around, which is fine because that's addition. Now, To me, this way seems a whole lot easier to do at the beginning, to me. I don't like waiting to the end to factor out a -1. I like factoring out the negative at the beginning, making sure your largest power is positive. It's way easier to factor, especially if you have to use a diamond problem, and we end up getting the right answer without a whole lot of extra work. Do you see the point in that? So that statement I made last part of class, factor so you get the term with the largest exponent positive. It's kind of a nice easy deal for us. Okay, let's go ahead and move on. What I'd like to do, I would like to give you a couple examples on your own. Are you ready for a couple examples on your own? One's going to kind of refresh your memory about what we did yesterday, and one's going to be similar to this year. Okay, so I'd like to do that, factor that one, and simplify, and then do this one. And if you want to be brave after that and finish these things early, there's another one we're going to do together right now. I'm actually going to go through and show you how to factor a sum of cubes in a problem. So in each case, we're trying to factor the numerator and the denominator completely. That's very important. Now, we're going to try to factor to keep the term with the largest exponent positive. If the term with the largest exponent is already positive, well, that's great. You don't need to factor out a negative. But if it's not, then you're going to want to factor out a negative. That's the whole idea here. We'll give you about 1 more minute. Let's see how far we can get in 1 more minute. Okay, we're going to get started if you're on the first one. If you're still working on the second one, that's okay. If you're on the third one, that's great. You know how to do that one. That's awesome. That's the different. That's the one of those cubes that we were talking about. So on the first example, of course, on the denominator we can't factor that. It's going to stay the same. Hopefully, we're going to simplify that out. On the numerator, though, there are something we can factor out. Now the question is, do I need to factor out a negative or not?
No.
Do you see how the largest term is already positive? The largest term, the exponent with the largest term is already positive. That's what we want to happen. So we don't need to factor out a negative there. That's fine. So we're just going to factor out what? 3. Great. Any x's? You're going to take the biggest one that's common to both. What's that? And what we have remaining is, did you get that far? How many did? Good. All right. On the denominator, we have 3x to the third. Does anything simplify? This is like one of those ones we had yesterday, only kind of in reverse, actually. It's good. Yeah, 3's are definitely gone. The x to the cube and x to the fourth, we can also simplify that. Okay, those are factors in this case. So x to the third is gone. The x to the fourth becomes just x to the first power. Just don't forget about that. Remember to write that x. So here we're going to have x, 3x minus 1. You can put it over 1 if you'd like to, but since this is some expression over 1, you really don't need that 1. So if you get this far, you're done. How many people did get that far in that problem? That's good. If you didn't, check this problem out later. Make sure you can do this. Make sure you can get down that far. Are you guys okay on this one? Do you have any questions on this one?
So if you put it over 1, you would still accept it as correct?
If you put it over 1, I would like for you to see that the 1 is really irrelevant here.
So it's not necessary.
Yeah. Under 1, that's a different story. Okay, that's important.
Right.
But over 1, it's like doing this. My answer is 4 over 1. What's your actual answer? You say 4. Now, if your answer was 1 over 4, okay, you say my answer's 4? No, it's a different story. So if it's over 1 like that, you really don't need the 1. Okay, if it's under 1, yeah, you certainly need the 1. Okay, that's the difference. So our answer here is just like that. I'm not sure if you're okay with that. Yeah? Right. Now the next one's a little bit more work. Next one says, let's look at the numerator. Notice how our x squared term, the term with the largest power, has a minus in front of it, or what we consider to be the negative root of that term. What we're going to do here, what that tells me to do, you're going to factor out a negative. Did you try to factor out a negative from that? Negative what? So if we factor out negative 3, you'll get, from here you'll get negative 1, from here you'll get plus x squared. Do you see why the signs change? You see why the signs change, folks? Factor in that negative. Why did the top one do that? Well, because we didn't factor out a negative. We factored out the positive 3 instead of the negative 3. You see what I'm talking about? Here we're factoring out negative 3. We're dividing by a negative there. That's going to change these two inside signs. Here, we're not doing that. We're factoring out positive 3. Because the term with the large exponent is already positive. That's what we want to see. Okay. So, if your term with the large exponent is negative, like right here it is, x squared, it's negative, factor the negative. It's going to change the signs. Here, it's not. X to the 5th is positive. You leave it alone. You factor out just the regular whole number, no, not an integer. Okay, not a negative. Okay. Let's leave the denominator alone for a second. Let's work just on the numerator for now. We want to make sure we get this all the way down. So the negative 3 is going to stay there, but I am going to switch these things around. Instead of negative 1 plus x squared, I can write this as x squared minus 1. Are you okay with that? It's just the commutativity of these two terms. We can do that if we keep the signs with those terms. So the negative 1 has to be a minus 1. The plus x squared, that's a positive x squared. You still okay? What is this? How is it a difference of squares? X squared minus 1 squared. That's the same thing, isn't it? So if we factor that, this is certainly a difference of squares. This is going to be x minus 1, x plus 1. X minus 1, x plus 1. The way you can see it, it has two terms. There's a minus. This is something squared, and this can be written as something squared. 1 squared. That's trivial, but you can write it as 1 squared. If you can do that, you can factor it. The way you factor it was the a squared minus b squared. Look that up on lecture C.4 if you want. Actually, it's under C.1 on the lessons. And we do this a couple times in there. So we're not going to forget about this -3. We have factored this. And we're completely factored in the numerator. That's what we want to see. Now, can you raise your hand and feel okay about getting there? If not, are there questions that you have on this stuff? Do you see why we're doing this? Do you see why we're factoring out a negative? I hope so, because this term of the power is negative. We want to factor that out. Can you see why we're switching those two terms around? We want to write that in the correct order. We want to write the x squared first. That way we can factor it easier. Because when you see this, that eventually will be easy for you to factor. We go, oh yeah, it's x minus 1, x plus 1. No big deal. You won't even have to do this step. It'll be in your head. We do this, we're completely factored at the top. On the denominator, we have a basic diamond problem. We're not going to have an extra step. There's no number out front. We've got 1 and -2. The two numbers that I'm thinking of are 2 and 1 somehow. Did you find 2 and 1 somehow? Like that, probably. Or switch around. It really doesn't matter. So we'll go directly to the factors. We don't need to factor by grouping because there's no term out front. There's no coefficient up front. We continue on. We'll just keep writing that until we get down to the part where both of them are completely factored. So we just carried this one all the way through. Now, is there anything that we can simplify out of that? Yeah. And you know what? If you hadn't factored out this -3, you probably wouldn't see it immediately, and you'd have to factor out a -1 anyway. Do you guys get the picture on that? You have to do it anyway. So you may as well do it at the beginning, because it makes things a whole lot easier. So we're going to simplify out this -1. We'll rewrite exactly what we have. Left, -3 times x minus 1, or x plus 1. You don't have to distribute, just leave it factored. And then x plus 2. And you're done. As far as you can go. We can't simplify any x's or anything like that. We're done. Would you raise your hand if you're okay on these two problems? If you don't, if you're still a little lost, you're like, oh my gosh, come and see me or something. I'll walk through this with you. I'm in the math lab or office. You can always come by and see me. I haven't had very many people do that yet, but I'm there. I'm available to you if you need that resource. Okay, now this one's kind of an interesting one because what I told you is I'm not going to go over a sum of cubes or a difference of cubes in class. I want you to look at it. I hope that you did, because we're going to do this one right now. And guess what? That's two terms, right? That's not a difference of squares. It's not factored the same way. This is actually a sum of cubes. That's a cube. Can this be written as a cube? Yeah. Here's how you deal with a difference or sum of cubes. If you have something written as a cubed plus b cubed. I've given this to you in class. You don't need to rewrite it. It's in your notes somewhere. You write this as a plus b. Remember the same sign, different sign thing? Same sign. The next part is a squared, different sign, minus ab plus b squared. So essentially, all you have to do is figure out what a and b are, then fill in this formula. It's a formula for you. Let's see if we can practice this on this example up here. Instead of x cubed plus 27, instead of x cubed plus 27, can you tell me again how I can write that? As this form, something cubed plus something cubed. Okay, so the x cubed stays the same. 3 cubed instead of 27. Do you see how this is 27? It's not 9, right? No, just multiply those things. It's 3 times 3 times 3, that gives us 27. You with me so far? So you see how this fits in this formula, right? Okay, what's our a in our case? What's our b in our case? Let's fill that out. All you have to do is replace a with x and b with 3. And it'll work itself out. Watch. I'm sorry, what was a again? Plus, what was b? Okay. Now in the next part, we're going to fill this out. What was a again? So we're going to put x squared. You see what's squared, right? minus, what was A again? What was B? Times 3. We're going to rewrite this in just a second. We don't write x3, do we?
No.
3x. That's not a problem, no. Plus b squared. B squared, how much is b again? So we're going to write 3 squared. That's how you use the sum of the cubes idea. The difference of cubes is exactly the same. It's just this becomes a minus, a minus, a plus, and a plus for a difference of cubes. Sum of cubes, that's with this plus. If this was a minus, these two signs would switch. That's the only difference there. So hopefully you can draw some conclusions from this example for that. So x plus 3, that's done. X squared, well, that's done. We're going to rewrite this a little bit. We're going to do 3x, and at the very end, we're going to do so we have just completely factored the numerator. Can't go any further on this thing. We're going to have, instead of x cubed plus 27, this sum of cubes worked for us. We're going to have x plus 3, x squared minus 3x plus 9, all over, what's the denominator still? We couldn't simplify that. Does anything simplify? That's great. We got two complete factors that are there on the same, on the numerator denominator. We can simplify out the x plus 3. Are you with me on this one? You sure? Fancy math, right? But it's just a formula. I mean, it works. Well, I've given this to you before. We just haven't done it in class. So our answer is x squared minus 3x plus 9. Of course, that would be over 1, but the 1 doesn't matter, so we're just going to leave it like this. Yes, that one. Simplify, you mean like factor it even more? Well, you can try it, right? That would be a diamond problem. But what you're thinking of is two numbers that add to negative 3 and multiply to positive 9. The only things I can think of that multiply to 9 are like 3 and 3 or 9 and 1, right? And none of those are going to add to negative 3. So you can't factor it anymore. This is one of the 3-term polynomials that you can't factor. You know, not all of them you can. So some of these things that look like this, you might not be able to factor. It all depends on whether you can find these two numbers. If you can, you can factor it. If you can't, that's a good question. Any other questions before we go on? Were you able to follow that one? That's good. That's kind of advanced stuff. That's difference of cubes and sum of cube stuff. That's good for you. Fantastic. Okay, one more thing in our section, then we'll move on to 7.2 and have some real fun. Are you ready for some real fun? Of course you are. Fun Friday, right? Oh, it's Fraction Friday. See, I knew there was something good about today. Okay. Some of you are like, I hate you. Not only do you make us do fractions, you make stupid jokes about them. I know. Ruin my Fridays. That's what I do to you. Okay, yeah, you're welcome. Welcome. That's all. Last one I want to show you before we move on. X squared plus 6. Let's do that one over. That. Let's do this one together. We're going to go through it kind of quickly because there's just one thing I really want you to see about it. Let's look at the numerator and the denominator. Of course, we're trying to factor this completely. Look at the numerator. What factors out of the numerator, please? 3. Do I need to factor a negative 3 or not? What do you think? No. That's already positive. Don't worry about that. Factor the 3 out. We get x squared plus 2. Did you get x squared plus 2? One question I have for you is x squared plus 2 factorable? X squared plus 2, absolutely not. No, it's not a difference of squares. It doesn't have a cube, so it doesn't fall into this category. You with me on this? Can't do anything with that. That's done. So we look at the denominator. How many terms are in the denominator? 4. Don't forget what we do with 4 terms. Say that louder. That's the only thing we can do. So in this class, when we have 4 terms, you are grouping. So that's the only thing we can try is to group this thing. Remember how to group? You don't group, look at the board real quick. You don't group the first three. You don't do that. What you do is you group the first two and the second two. That's how grouping works. The first three, this thing's going to be left by itself. You're not going to know what to do with that. So you factor by grouping the first two and the second two. What factors out of the first two, please? And we're going to get x minus 3. Out of here, we have a positive, so we're factoring a positive 2, and we get x minus 3. Does it look like it's going to work for us?
Yes.
Yeah, if these aren't exactly the same, it's not going to work. But here, we've done this a lot now. We use this every time we have an extra step in a trinomial, a 3-term polynomial. So we're going to factor the x minus 3. What's left when I factor out the x minus 3? Can you tell me that? Perfect. So on our denominator, we have our x minus 3, x squared plus 2. So just a little recap. Out of the numerator, the only thing we can do is factor 3, and we're done with the numerator. There's nothing else we can do. On the denominator, whenever you see 4 terms, the thing you're going to try to do is factor with grouping. That's it. So factoring by grouping means the first 2, x squared comes out of that, no problem. Second 2, only 2 comes out of that, no problem. When you have exactly the same thing, you factor it out. You write what's remaining in your second parentheses, just like we do with the extra step on the diamond method. That's really the exact same thing we're doing here. The terms are a little different, but the same idea. And that is our new denominator. Does anything simplify? Perfect. We got that. We'll write what's remaining. That's a 3 over x minus 3. And now the 3 is simplified, right? Why am I not writing? Those are terms, they're not factors. So I cannot simplify those 3s. Are you with me on this? I get students in calculus who still do that. It makes me so mad. Go, no! Your paper's screaming at me. What? It makes me cry a little bit. All right. Oh yeah, there's one more thing I need you to know about fractions. Here's the thing I need you to know. I need you to know that this, it's supposed to be A. Kind of. This is the same as, whenever you put this negative, it really doesn't matter in a fraction. So you can have a negative out front of a fraction, or on the top of a fraction, or the bottom of a fraction, and it means exactly the same thing. Did you know that already? So there's some equivalent forms of fractions that you're going to be dealing with. And essentially all it's going to ask you to do is move the negative from the middle to the top to the bottom. Just move it around and see that you can get different looking fractions that have the same value. Does that make sense to you? Different looking fractions that have the same value. That's going to be the little process you're going to do in the last part of this section. Now, how many people feel comfortable with simplifying fractions? You okay with this? So we're factoring. Is that the hand raising? I love it. It's so lazy. So we're all going to do this now. So we've done the simplifying fraction. I was just kidding, by the way. You know that. We've done the simplifying these fraction things. We know we factor, and then we simplify out common factors. That's what we do. If you know how to do that, the next section, which is multiply and divide, becomes very, very easy. I'll show that to you right now. So we're going to go on to section 7.2. For the rest of our time, we'll talk about how to multiply and divide rational expressions. That just means fractions and polynomials, just like we've been dealing with. Multiplying and dividing rational expressions. Multiplying and dividing rational expressions. Very, very, very much like working with fractions. With fractions, you really have two options, right? Here's your two options for multiplying. If I just give you some regular old fractions, we can do something like that. And you have two options, really. You could go and multiply the numerators, couldn't you? Do like 7 times 15, 5 times 11, because we know when we multiply fractions, we just go straight across. Do you recall that from a long time ago? I hope so. I hope you do, right? Yeah, that's good. We just go straight across, and we get something like 100, what is that, 105 over 55. And then you have to simplify it, wouldn't you, if you did this way? But there's really another option. This is probably what you prefer to do when you multiply fractions. So the or, when you get down to this part, multiplying and dividing rational expressions. Multiplying and dividing rational expressions. Very, very, very much like working with fractions. With fractions, you really have two options, right? Here's your two options for multiplying. If I just give you some regular old fractions, we can do something like that. And you have two options, really. You could go and multiply the numerators, couldn't you? Do like 7 times 15, 5 times 11, because we know when we multiply fractions, we just go straight across. Do you recall that from a long time ago? I hope so. I hope you do, right? Yeah, that's good. We just go straight across, and we get something like 100, what is that, 105 over 55. And then you have to simplify it, wouldn't you, if you did this way? But there's really another option. This is probably what you prefer to do when you multiply fractions. So the or, what we're going to do, when you get down to this part of it, you still have to write it as 7 times 15 over 5 times 11. But what we can do here is, instead of actually going through with this process, I want you to realize what we've just done. Look at the problem real quick. Do you see that in going from this step to this step, we've actually changed it from a multiplication problem to a simplification problem that we've just done? Do you see that? Do you see common factors now? We can simplify common factors. So the 5 becomes a 1, 15 becomes a 3. This is what you're used to, right? I hope. And you do the 21 over 11, which is a lot easier than doing that. But notice that the process here is, when you write two fractions being multiplied together as one fraction, you change it from a multiplication problem to a simplification problem, and then we're back to the 7.1 step that we just finished doing. That's it. That's really it. We'll try a few kind of basic problems here, just to get our feet wet with the stuff, and then we'll deal with some honest to goodness rational expressions and see how they're observed. So just to kind of confirm what we're doing, can we do something like, Okay, first thing. Notice we do have multiplication. They're fractions. They're rational expressions. We only have one term on each numerator and denominator, though. That's fine. We can still go about and multiply these together and simplify. So here's what we're going to do. Here's a step I do need to see from you. Are you listening back there? Step I do need to see from you. I need to see somehow that you're making this into one fraction before you start simplifying them. This is for a couple reasons. First, I need to see that you know we multiply straight across, and we get one fraction on the top and the bottom, numerator and denominator, before we simplify. Second, I can't allow you to do this across like addition or subtraction because it just flat out doesn't work. And so if you can make this into one fraction, write this as one fraction, then I know you understand that I'm not going to be able to do this on addition subtraction. We can't simplify across addition subtraction. Are you with me on this? So there's two ways you can do this. You can rewrite the problem like I'll be doing, or if you just don't feel like rewriting it, if you ever have multiplication, we can just extend that line and put the dot on the dot. That makes this into one fraction. Just do this little piece before you actually simplify it. You okay with that? Just do that for me. Make sure you have one fraction before you simplify, because if you can't do that with addition or subtraction, you got a problem. You can't simplify like we're about to. So I'll go back to what we were. You can just do the line, put the dot in the dot if you'd like on your paper. Me, I'm going to rewrite it. Negative 5x cubed. We know with multiplication we multiply straight across. So this becomes negative 5x cubed times 2b squared. We're actually not going to multiply them together. We're not going to get negative 10x cubed b squared. That's too much work. We want to simplify before we do that. So let's look at this problem. What I'd like to know from you is, do I have any common factors on the numerator and the denominator? Firstly, are you okay getting to this point? Yeah. Multiplying fractions is straight across. We're right here right now. We haven't multiplied the numbers yet. We're right here right now. We're going to simplify now. What was the numbers you said? 5. Okay. So we're going to simplify like you would up here. The 5, negative 5 becomes a what now? 1. Yeah, don't forget about the negative, negative 1. And this 15 becomes, and we're divided by 5, remember. What else gets simplified? Oh, x is great. This x is completely gone. This x becomes what? I'll write that up top so I don't forget about it. Anything else? Oh, b's, okay. So the b squared and the b cubed, what happens here? Gone, okay, great. And this becomes a what? So I'll rewrite that. We just have to be careful not to lose anything in translation here. So we notice we have a negative. We've got an x squared, and we have a 2. Don't forget about that 2. You didn't cross it out. It's still there, right? Can you tell me how much I'm going to have on the numerator? Great. Perfect. That's exactly right. Negative 2, x squared. It's all being multiplied. And on the denominator, how much do you have? How'd you get the 9?
Because 3 times 3 was
So we don't forget about that 3. We didn't cross that out. It's still there. 3 times 3, and then the b. You're exactly right. Would you raise your hand if you're okay with this one? Feel all right with it? Would you like to try one of your own? Sure. Let's try it. We'll try 2. One, you might not be able to simplify it. I just want to make sure that you can do this. The second one, you'll be able to simplify. There we are. So let's do this on your own. Remember, what I'd like to see from you is before you try to simplify or even multiply these things together, I want to see you write this as one fraction. So if you want to just extend that line, that's okay. That's fine with me. As long as we know that we can't simplify until we get this to be one fraction. That saves a lot of headaches later. Is there a little bit more time? Give it 20 more seconds so see if we can wrap that up. Good, that's a good work so far. Okay, here's what I'm talking about showing me the work. If you really want to do this, if you don't want to rewrite it, write this as one fraction because we can do that with multiplication, with a dot and a dot, signifying that multiplication of two fractions is multiplication of numerators and denominators. That's fine with me, okay, if you do that. Then check for anything you can simplify. Is there anything to simplify in this problem? No, there's really not. So we're going to keep on going and say this is 12a, this is 5b squared, and that's it. Sometimes you can't simplify anything. If there's no common factors, you're good. That's it. The next one, same idea. We'll extend our fraction. Did you do that? With the dot and the dot. I want to see that because this shows me I understand it has to be one fraction before I start crossing stuff out. Anything simplified here?
Y squared.
Okay, y squared is gone. Y cubed becomes a
Y.
Perfect. Anything else?
And
3 is gone. That becomes a 1 actually. And the negative 9 becomes
3.
good. Don't forget about the negative. Right. We have x to the 4th and we have an x to the 5th. X to the 4th is completely gone, becomes a 1. X to the 5th, we have 1 remaining x after we. Alright, what's left over? Right, nice and neat like. We've got 1 times 2 times y, so that's going to give us 2y. We've got negative 3 times x, that's just negative 3x. I believe that's our final answer. As good as we can do it. Now, there is one more that we can cover today that we're going to talk about. What happens when I start doing things like this? A rational expression times a rational expression. Well, guess what? This is going to be so simple, simplification is not even funny. It's going to be almost the same thing. There's only one little extra step that we need to do. So here's our steps for this. First step we're going to do. Pretty much this happens almost every time you get rational expressions. What's the first thing you think we're going to do? What shoes are you wearing today? Factoring shoes. What are we going to do? You're going to factor. You're going to factor this. Just like you did with simplification, you're going to factor completely. Factor completely. Let's see if we can do that. Just kind of do this quickly. We have a minute and 10 seconds to see if we can get this thing done. Does this factor? What factors out of that? Perfect. Does the 7 factor? Does the 14 factor? Hey, are you starting to recognize what the x squared minus 1 is? What is that?
It's 1.
Good. Different square someone said over here, x minus 1, x plus 1. Are you starting to see the x minus 1, x plus 1 pop up like that? factor this, factor that 6. 7 and 14, we're good. X squared minus 1, we've got to factor that difference of squares. Remember, this is x squared minus 1 squared. We can do x minus 1, x plus 1. We already did this today, actually, in this class. The next step is exactly what we did right here and right here. We're going to write this as one fraction. That's the easy. That's easy. For us, that just means this right here, folks. We're going to take this. We're going to extend the line. That makes it one fraction. Put the dot dot. And guess what? Look at the border. Does this not look exactly like what we had in simplification? Because it is exactly what we had in simplification. Third step is simplify. If we simplify, can you tell me some things to simplify here? Gone. 7 becomes a 1, 14 is a 2. So on our numerator, we have 6 times 2, and we have x minus 1. That's it. It's completely simplified. How many feel okay with this problem? Good for you. That's our steps. We're going to be doing this a lot. Next time, I'll show you division as well. I believe I gave you your homework for 7.1, didn't I? Okay. Have you made it to the internet yet to find that? All right. So we're continuing learning how to multiply and okay. Have you made it to the internet yet to find that? Multiply, and then we'll get to divide into rational expressions. Today we'll continue with a couple more multiplying. The last one I gave you was the one with some steps on that, right? I gave you the steps as well. And the first thing that we're supposed to do when we're multiplying some rational expressions is we need to factor these things completely out. And the reason why is because we're going to be simplifying using common factors. So we can't do that unless we actually factor it. So let's go ahead and try this on this next example. Now we'll see what to do about this. Now I gave you a few steps last time. We're going to follow those pretty much to the letter every time we do a multiplication of rational expressions. That's the best way to do it. So the very first thing we get to do is we look at this thing and we are going to, what was that again? Yeah, we've got to factor completely. Because again, we're going to be looking for common factors eventually. So let's look at this thing together. Can you tell me something up here that you're going to be able to factor? Okay, factor out first before we start simplifying. Factor out. So, okay. So x squared minus 1, we can factor that thing. What's that called, people on the left-hand side of the room? This particular type of expression is? Let's square something. We have, that's a difference of squared. Are you guys awake today? Are you sure? That's a bunch of, all right, let's wake it up. Come on. Yeah, that's a difference of squares. You need to be seeing that. It's a difference because it has a subtraction. That's 2 squares there. We've actually factored that one at least twice in this class already. We need to be very good at seeing those. So we're going to, how about the 15? Can I factor the 15?
No.
How about the 5x? Can I factor the 5x?
No.
Those are there. Those are just single terms. You can't factor single terms. X squared minus 1, though, that is something we can factor. Someone in the middle of the classroom, tell me how I factor x squared minus 1, please. Very good. That's the difference of squares. It's got to be, bam, just getting those right all the time. Are you okay on getting x minus 1, x plus 1? See where that's coming from? Good, all right. We've covered that a few times in here now. Now, how about anything else up here? What else factors? Great, x squared minus x, what factors out of that? So remember, even though it looks like two terms, like that's not a difference of squares. How much does a factor that? We always start factoring with GCF, that greatest common factor. And when you look at x squared minus x, well, they share an x in common, so we're going to factor that out. So factor out an x. What are we left with if we factor out the x? Okay. You don't account factoring and things like that. Good. So no diamond problems here. That's really not a big deal. The next thing we do is, after we factor, what am I making you do before we do anything else? Say that louder. Yeah, we have to. Because what we're doing here is we're changing, after we factor, we're changing a multiplication problem into a simplification problem. And the only thing that we have to do to show that is I let you, instead of rewrite the whole thing, just extend that line. That's all you got to do. Because as soon as we extend that line, put the multiplication there and there, we now have a simplification instead of a multiplication problem. That's kind of nice. So now we're on to simplifying. So this is the best part. We get to cross stuff out. What can we cross out on this problem? Yeah, now we're ready to cross out the 5. We couldn't do it before because notice they're not together yet. We want to factor first, make sure we have this one fraction, then we can do it. The 5 with the what? 15 becomes a what, everybody? 3. Good. Okay, somebody else give me another thing I can cross out. Say that louder. The x. Let's look at the x. Can I cross out the x? They're being multiplied, right? That means it's a factor. So this x and this x are gone. That's great. Right-hand side of the room, something else I can simplify. Perfect. Those are entire factors. We can simplify those out. We're going to write what's remaining. We've got to be careful not to write anything we've crossed out, but we can't miss anything either. So on our numerator, what's left? Well, that's great. How about the denominator? So all this stuff, when you all simplify it, it's just equal to 3 over x plus 1. That's it. That's as far as we can go. You can't simplify anymore because you wouldn't have been able to do it in the previous step right there. How many people feel okay about this particular problem? Good. All right. Let's continue on this stuff. We'll do one more together, then we'll start talking about some division, and you're going to find that division is very, very similar to multiplication. There's one little extra step. I am going to have you do some of this stuff on your own on this problem. Okay, we are going to do this somewhat together, somewhat on your own. This is a great problem for us to do. This actually covers pretty much every type of factoring we've done here so far. So if you can do this problem, you should feel pretty good about your factoring, all right? So let's go ahead, and I'm going to do this piece by piece with you. We'll start with the easy parts of this. So right now on your paper, the first thing we know we need to do is factor. You guys are all with me on that, right? We can't really do anything with this unless we factor. We can't start simplifying 3 and 9. That doesn't work. You got to factor first because you have to get this as one fraction and then start simplifying. So what I'd like you to do is start with your problem, factor this one first. I'll give you about, this is an easy one, let's factor this one, about 5 seconds to factor that. Okay, so the 4x plus 8, I'm giving you some time. What factors out of 4x plus 8? Good. And you're left with? How did you factor that out? You got X plus 2. Good, okay. Now let's go down to, let's see, which one do you want to do next? This one. Okay, let's factor that one. Now there was one thing I told you about that one. Let's see if you can see it. It was about this, I think last time or something before that. Factor on your own, see what you can factor out. Okay, so 14x minus 7x squared, you have a couple options here, all right? You have options. Now, one of them is going to be a better option for you. I told you this a while back. I said you're supposed to factor in order to get the term with the largest exponent positive, because otherwise you're going to have to factor out a negative anyway. Are you with me on this? So in this problem, really, you shouldn't be looking at factoring out 7x. You should be factoring out negative 7x. How many people saw the negative 7x there? Good for you. If you didn't, now fix the problem. So we're going to factor out negative 7 and the x. If you do that, factor out negative 7x, what you're going to be left with is negative 2 plus x. Do you see how by factoring out the negative, we changed both signs? Are you clear on that or no? Are you sure? Okay. I just want to make sure that you know why that's a negative and why that's now a plus. Do you see it? So factoring the negative out. If you distributed it, we can get exactly that thing back in. Now the next step I'm going to do on this little part is I'm just going to take these and flip them around. It's going to be x minus 2. Now you're going to be okay on that part. Okay, that's going to make things a lot easier to see in the future in the next thing we're going to do. Okay, let's go down to, let's do this one. Let's do the 3x squared minus 5x minus 2. Y'all should know how to factor that one real well at this point. This is what type of problem? Good. And ladies and gentlemen, on the left-hand side of the room, is this going to be the extra step where we have to factor by grouping or not? Okay, do that now. I'll give you about a minute. You should be pretty good at this stuff right now. Also, guys, try to go through that homework kind of quickly because I have 4 assignments to get back to you. If we don't do it now, it's going to be backed up. Okay, hey everybody, what number goes up top? Okay, what number goes on the bottom? So to add -5, you're supposed to multiply to -6. Yeah, a lot of people try 2s and 3s here. 2s and 3s aren't going to work. You're going to have to multiply to -6. That means you're going to have 1 positive, 1 negative, and they're going to have to add a -5. 3s and 3s won't cut it for you. So you're going to have a 6 and a 1 somehow. In our case, we're going to have a -6 and a positive 1. -6 and positive 1 is the only 2 numbers that you're good. Did you find -6, positive 1? Good, all right. Now, we can't just put x minus 6 and x plus 1. We can do that if there's no number out front like that. That'd be great. But there is a number out front. That means continue on. And that's our new numerator. How many were with us so far? Feel like this? Good. Hey, there's one more part. Let's look at 9x squared minus 1. Back there. Some people already back there. That's good. If we factor 9x squared minus 1, we look at this and we see we have how many terms here? How many terms here? 2 terms. That means we look for greater common factor. Of course, there's not one because we have a 1 up there. But this isn't a diamond problem. This can only be really one thing for us. This could be a difference of squares. If it's a square, not a cube, or nothing. In this case, this is a difference of squares. Did you see the difference of squares? Now, how in the world is it a difference of squares? Well, squared. Do you buy that? That's 9x squared. And then minus, instead of 1, you really could, you could write 1 squared. And so what this is exactly the same with this. This is the same as this, basically. It's just instead of x squared, we have 3x squared. Are you with me on that? Difference of squares, we've had that several times now. You're gonna be pretty good at this at the end of the semester. So we get to factor this as 3x minus 1, 3x plus 1, just like we did this. Ladies and gentlemen, are we okay on the problem or no? Let's know if you're okay. You follow it down. You might have to go back and try this problem on your own. Trust me, you don't want to just sit here and follow it one time because, of course, I know how to do this stuff, right? It's going to make sense when I'm doing it, but it might not make sense when you're doing it. So go home and try this one again. make sure you can get this again, okay? If you're not doing it, I had a snafu with the lectures. I couldn't get them on this weekend. The hard drive just didn't matter. I was not so happy last night, but these will be on probably tomorrow afternoon, the lectures.
Can you write the negative 7x times the negative 2 plus x as x minus 2?
That's exactly the next step I'm going to do. Yeah, that's a great point. So, are you okay getting down to this far so far? Okay. So the next thing we are going to do is exactly what you said. Harpreet, right? Okay. What Harpreet said is, can't we write this a little bit different? And yeah, we're going to. Instead of negative 2 plus x, I'm going to keep the signs with the terms and just do x minus 2. So I'm going to give you the next step I'm going to do. Before that, before I start simplifying some things, I'm going to do one more thing. Yeah, I need to see one fraction out of this, so I'm going to extend this, put the dot dot. That's the only thing. I just want one fraction right there. That's it. And then we can start simplifying, shout out some things that we can simplify up here.
X minus 2.
Okay, someone else give me something else we can simplify up here. Great. Wait a second. Even though they're on the same fraction, I can still simplify those? Sure, why not? Yeah, you're just looking for common factors. It doesn't really matter. It doesn't have to be across from each other. Is there anything else we can simplify up here? I got 4. Is that this x? These x's okay? No. Okay. X plus 2? No, it's none of those. 3x minus 1 is nothing like that. So we're just going to write what's left over. We've got a 4 and x plus 2. We've got a negative 7x. 3x minus 1, don't distribute it, you just leave it, just like that. Now again, the reason why we factored out the negative 7 up here is so these two expressions would simplify out. Otherwise, you would have to factor a negative at this point. Are you with me on that? You'd have to do it somewhere. You may as well do it again, it's easier that way. Do you feel okay about multiplication today? Raise your hand if you feel okay about multiplication today. Good. So we learned that multiplication is basically simplification. It just happens in 2 different fractions. So we're simplifying 2 different problems at once, basically. We get to put them together as one fraction, and then we go. Let's see what happens now with some division. Just like before, we're going to start kind of nice and easy with some basic fractions here. And the question is, I know you know this because you're in this class, but how in the world do you divide fractions? Is there a way to actually directly divide fractions, or do we have to manipulate this somehow? Yeah, you really can't just directly divide them, right? It's really hard to think about that. If you really think about what's 3/4 divided into 7/8 parts, that's kind of weird to even contemplate that. But we have a method of doing this thing. What's the method of actually dividing our fractions here? Do what now? Flip one. Okay, yeah, that's great. We flip one. What's the flip one? What's that called? So we're going to find the reciprocal. We're going to reciprocate it. Reciprocate that fraction. Now, do we reciprocate the first one, the second one, or both of them? Which? Let's reciprocate that one. So we reciprocate the second fraction, and after we reciprocate the second fraction, we do what to it? Yeah, multiply it, and then we'll write one fraction. So we're learning that division literally has one more step than multiplication. That's really it. And it's not even a hard step. You just have to remember to reciprocate the second fraction. Then you're back to multiplication, which we just finished covering, which essentially is just simplification, which is basically just factoring. So if you know how to put fraction and factors, you're done. That's it. So we're going to reciprocate second fraction. case up here, what we do, like you've seen many times before, we leave the 3/4. Instead of 7/8, we make that 8/7. That's the reciprocal. And then that changes division into our multiplication. That's great. Because as soon as we do our multiplication, we know we can extend the line. We put the dot, dot. We can simplify it. Simplify like we've been doing for a long time. We get 6/7. If I've done that right, I think I have. And we're good to go. Be okay with the division of simple fractions like that? Good. Let's try to extend this concept to our rational expressions. So 7x squared divided by 6 divided by x over 2y. And our first step again is, what's our first step? Reciprocal. Okay, so we're going to find the reciprocal of, again, we're talking about which fraction here? Let's do that. So the reciprocal just means we're going to leave the 7x squared alone over 6. Instead of dividing, we'll be multiplying, and we're going to flip over or reciprocate the second fraction. And this is something we just finished doing. That's great. We know how to do that. What's the first step in doing this one? What was that again? Good. Okay, we want one fraction out of it before we start simplifying. So we're just going to continue that concept. We make one fraction. And if someone who hasn't spoken yet today, what's the first thing I can simplify here? Say that again? 7x squared. Okay, what part of that? Okay. X squared becomes what? And what else happens? Good, okay. Anything else that you see? 2 becomes, 6 becomes, perfect. Anything else that you see? Anything else? No, I think we're done there. We're going to write the numerator as the multiplication of those remaining factors. Denominator, same thing. So we have a 7, we have an x, we have a y. All of the 3. That's it, as far as we can go. Let's try one on your own before we make this any more complicated. Just make sure you have this down, then we'll keep going, okay? There we are. Is that homework still going around? Have you guys got the first assignment yet?
No.
Okay, perfect. What's the first thing you did? Okay. Do you know, by the way, why I have you wait until you have one line before you simplify? Here's a good reason why. Because if I don't have you do that, a lot of times people look at this fraction and they go, oh, you know what I see? I see the 10 over 24. I can simplify that. You see how if I don't have you write one line, then some people are going to do that. See what I'm talking about? You know, oh, 10 24 goes in, 2 goes in the middle. We get 5, we get 6, or we get 12. Yay! But we can't do that here. We have to wait until we can write it as one fraction. That only happens on multiplication. That's why I had to do that step. So here we go, all right. First thing we're going to do is reciprocate the second fraction. Of course, we're going to be multiplying, but now we're going to be multiplying by 6 over 10, a to the 5th. Nod your head if you did that step correctly. Sweet, good deal. Next thing we do is what? Before we simplify. Yeah, before we do that, I want to see that. This allows you to simplify things. It says, oh, I have one fraction. One fraction is how we simplify. Common factors both top and bottom. We do that part. And now we need to go, okay, the things I see here are 6/24. 1, 4. Did you get that one? We have the 5 and the 10. 1, 2. I got the a to the 5th and the a cubed. A cubed's gone. A to the 5th becomes a squared. And what I'm hoping is that you got a b squared over 8a squared. Did you get that as well? And we're done. As far as you can go on that problem, okay? Now let's see what happens. See if we even do anything different when we start getting actual, honest to goodness rational expressions. So this has some pretty serious factoring in it. We're gonna have to do that. But here's what I'd like from y'all, right? Y'all know that we're gonna factor here, right? Right? You're gonna factor eventually. That's what this whole thing's about. Just make sure that you flip it first before you factor it, because what I would hate for you to do is factor and then notice some common factors that maybe are coincidental and simplify those before you flip it. That would be the wrong thing. So make sure that we're flipping this first, and then you can start factoring it. Are you with me on this? Just do that first so that we have that down. So I'll say flip first, then factor. So the first thing we're going to do, we leave the first fraction alone. We all know that by this point. We're going to change our division to multiplication by reciprocating the second fraction. And then we get to factor it. Why don't you give yourself a few seconds to try to factor that thing, okay?